Okay, so I believe that it actually is 10:30. So hello everyone. Thank you so much for joining us today for what we hope will be an exciting webinar. So to respect everyone's time, we will actually start on time instead of what happens at my institute where we start precisely 5 minutes late. So to get started, I'll give you just a brief introduction of who we are, introduce our panelists, and then we'll get started. I've tried to reserve a lot of time for discussion between the panelists as well as discussion time for you, the audience and participants, to ask questions of our panelists. So with that, a little bit of introduction. So my name is William Ratcliffe. I am the PI, one of a few PIs on a grant from the American Physical Society to try to get more data science into the physics curriculum. And so this is occurring as part of that grant. I am also the vice chair of the APS topical group on data science. And part of this is, through the efforts of our topical group. Besides myself, we have Wolfgang Lacerte, who is the past chair of the topical group on data science. Wolfgang, if you want to wave your hands. We also have Mohammed Saltina, where he's the founder of the topical group on data science and one of our panelists today. We also have Alexis Knob, who is another co-PI for this grant, along with Marlena, who will be joining us. She's kind of stuck on a train. If you'd like to join the topical group on data science, we have a channel that is completely devoted to these issues of data science education and physics. And so we'd be happy to have you join. You can follow the QR code. We also have a mailing list, again, for this project. And so if you aren't on our mailing list or don't know if you're on our mailing list, you can just click on the link that will be in the chat to join the mailing list. Again, it'll be a low volume mailing list, so don't worry about getting too spammed. You can opt out at any time. One bit of administration is that we will be allowing you to ask questions on an application called Slido, where you can vote up or down questions. Given the number of participants that we're expecting, this will be much easier than trying to surface questions from the chat. It's also been noted that this is recorded and we plan to post it on YouTube. All right, so one other bit of housekeeping, but a very important bit of housekeeping, is that for this meeting, we will generally follow the APS Code of Conduct. Please just take a moment to familiarize yourself with it if you're not, but basically be nice to each other. If you have questions about ideas, you can be hard on ideas, but be gentle on people. Again, just take a moment, familiarize yourself with the code of conduct. We will take that seriously. We want to have a community where people are feeling welcome and that communication is civil. All right, and so with that, I think that we're actually amazingly close to on time. And so we'll soon get started with the panel. And so our first speaker will be Trevor Rohn. With that, let me stop sharing my screen. And let's see, Trevor, would you like to share your screen?
Yes, thanks. I'll do that presently. Hopefully you can see my slides.
Yes, and just you can read the full bios of our speakers on the webinar announcement. But Trevor is a professor where at RPI, where he does research at the intersection of material science and artificial intelligence. And he also does a lot of work with the teaching of data science. And so we'll start with some of his thoughts on data science education in the physics context.
Good morning, everyone. It's nice to meet you all. Thanks, William and DDS for having me. It's really a pleasure. When I started doing data science work just after grad school, getting my first postdoc, I didn't really have any idea of what to do, where to go. This was back in 2012 or thereabouts. And this was when the community was just getting started. And so I had a really tough time about learning these things. And so empathetic toward people who want to learn about data science or physicists, but not quite sure where to go. So this kind of motivates that. So once I kind of learned what I was doing, I started giving physics research talks where I would explain the steps of the data science process and encourage people to become data scientists or to incorporate data science into their research. I also had the pleasure of giving a data science education talk hosted by GDS at a March meeting a couple of years ago. That was a lot of fun. Thanks again for that. And this I would call like your mid-range interactions for the physics enthusiasts among us. Next, I would have this kind of a shorter range interaction where I would design new courses for data science or with data science elements included, and interact with students and teach them principles of data science that they could apply to their physics research or to their future jobs in data science. I'm also having this apprenticeship route where I have 4 graduate students in my group and 6 thoroughly talented undergrads and 1 extremely talented high school student. And we're all getting trained in data science and principles and eventually going to apply data science to our research. In addition, we have a kind of a longer range interaction, and this is a kind of symbolizing that, where I'm going to start this data science YouTube channel, and I've already posted some information to this channel, so please take a look. In addition, people would ask me over the years, like, so how do I get started? And I started to kind of pool all those resources into a website. So if you travel to www.materialsintelligence.com, you'll navigate to a resources tab and find some resources that you can have access to. This first one here is describing is a link to the YouTube channel that I described a little bit earlier. For easy access to this, please use this QR code or visit the website shown here. Thanks.
All right, thank you so much, Trevor. So next up, we have my esteemed colleague, Gilad Kusni. So Gilad, do you want to share your screen? And so while he's doing that, Gilad is one of my coworkers from the National Institute of Standards and Technology, and he is also a professor at the University of Maryland, and he has been doing a great deal of research on using machine learning to perform experiments better, to do autonomous experimentation, to do phase diagram mappings, et cetera. And he also runs a boot camp on machine learning and materials science. So Gilad, can you tell us a bit? You're muted, Gilad.
Ha! Okay, I'm back. Okay, thank you. All right, I have a few things I wanted to discuss in very little time, so I'm going to run through them. But the first is, we have educational opportunities at NIST through internships, fellowships, and postdocs. We run this boot camp, which is the 7th or 8th year that we've been running it, along with mini boot camps. I'll talk about using Legos for machine learning, a competition, and then a website. So for internships and fellowships, we have a high school internship program at NIST, as well as one for undergrads. And then we have this 2-year postdoc through the NSF. So if anybody's interested, or anybody who's interested, please contact me about these. Then we also have the boot camp. So the boot camp is a 5-day hands-on tutorial. So it's 4 days of like hardcore hands-on, like actual boot camp type style education, where let's see, we'll pause. So we cover the wide range. We introduce machine learning from the beginning, from just an introduction to Python, all the way to how to build the machine learning necessary for an autonomous system. So we start off with describing data and data science. My computer is stalling. I don't know if that's, yeah. I'll just try to make it through these slides. So we do a day on unsupervised learning, a day on supervised learning, and then also a day on Gaussian processes, active learning, and autonomous systems. So how to build an autonomous system out of the tools that we've learned, through the boot camp. And through the whole boot camp, the focus is on providing collaboratory notebooks that allow you to very easily implement all of the tools that are taught. We also have a day where we have recent researchers come in and explain how they did step-by-step some of their recent work. And so our focus is on uncertainty quantification propagation, teaching the fundamentals of machine learning, and providing tools for all the attendees. We have a poster session and a hackathon, and we've had so far attendees from 24 countries, with about 30% attendee from industry. And we've also had mini boot camps that we've given at MRS, TMS, APS. We've provided a boot camp for NSF, and many other locations. So if anybody's interested, we can provide a short boot camp, which is less than a day, or 2 days, up to 2 days. And these include the hands-on tutorials. All those lessons have been integrated into a University of Maryland course. So this is, we're going on the 3rd year that we're going to teach this University of Maryland course on machine learning for the physical sciences. And as part of that, we've developed a small Lego system that allows kids to build an autonomous system themselves. And so it's a kit, and allows you for about under $300 to build a small chemistry autonomous system out of Legos. And we demonstrate it for a whole bunch of cool things, like discovering physical principles of the experiments that it's doing. And we're going to have a paper out on this soon. And if you're interested, I think, so we have these pop-ups. So there's a YouTube video showing, this is the system from about 6 months ago, and some of the machine learning that it's being used for. So if you're interested, I can share the link for this. Okay. And all the tools that we've developed are being curated on a website called REMI, the Resource for Materials Information, where we're also trying to curate all of the online resources that everybody else provides. So all the Collab notebooks for all the different platforms, including Citrin's platform, Materials Project, all the many platforms that exist outside, where we're trying to curate them in a searchable space. And here I can show that as well. If I can grab, this is really obnoxious. Okay. Yeah, okay, so this is the website, and you can see that there's this searchable, so you can search by data science tags, What instrument was the data collected on? Was it electron microscope or an X-ray diffraction system? Does it use DFT or does it use a real experimental data? What collection does it come from? So we provide this searchable database. And we've also started an annual competition, which we first ran at MRS, where we gave away a few $100s to the first prize, second place, and third place. Each person got a few $100s, I believe, which was sponsored by a publisher. And this is a competition where anybody can try to solve a machine learning challenge in material science. And we're also going to have a paper on this. And okay, so that's it. That's the full gamut of the content I have. Yeah.
All right. Thank you so much, Gilad. And next up, we'll have Frederica. Again, just a reminder, post your questions in Slido for the speakers. I see some already coming in, so I think we'll have a lively discussion. So next up we have Frederica. And so Frederica is an assistant professor at the University of Delaware, where she works on data-driven solutions to any number of exciting problems, some involving explosions. But in this context, she's going to tell us about data science education in the physics context. So with that, Frederica.
Thank you. Can you hear me?
Yes.
And can you see my slides?
Yeah, perfect.
Okay, great. So yes, thank you. I'm at the University of Delaware. I have a number of departmental affiliations. I have a bit of an unusual academic path. My primary appointment is with the Department of Physics and Astronomy, and the explosions are stellar explosions or supernovae. But I also am affiliated with the Biden School of Public Policy and Administration, and I'm a recruit of the University of Delaware Data Science Institute, and I wear a few hats in organizations such as the Rubin Observatory as well. The University of Delaware has a land acknowledgement, which in the interest of time, I won't be able to read in full, but I encourage you to see the land acknowledgement and the slides. I will read just the beginning and the end of the land acknowledgement, which says that the University of Delaware occupies land vital to the web of life of the Lenni Lenape and Antikoq, who share their ancestry, history, and future in this region. While the harm to indigenous people and their homelands are beyond repair, we commit to building right relationships going forward by collaborating with tribal leadership on actionable institutional steps. Okay, so on to data science. So like I said, I have a couple of different appointments. So my experience is perhaps a bit unusual. I was trained as an astrophysicist, and I always worked on data intensive problems and, before data science was trendy probably, and then straight into data science. But I also worked at the Center for Urban Science, and now at a Center School of Public Policy. So I've developed different modules for all of the departments that I've worked in. I'm going to list them here. I really started teaching data science with principles of urban informatics. The idea was to study city environments as complex systems through the tools of machine learning and data science. And there I had a very large class of students, class 2 sessions by about 50 every year. And it was a master level class. The challenge was that the background of these students was extremely diverse. And I sort of carried that and learned from that. And I really have, over time, try to focus on making data science education inclusive and accessible to all the students, whatever their background is and whatever they want to use data science for. So as I was recruited for the University of Delaware, I developed 2 data science classes for the University of Delaware: machine learning for time series analysis, which I'm teaching now. My slides are all out of order, and data science for natural sciences, which is also I think the technical name is data science for physical scientists, but in the interest of making it a little bit more broad and a little bit more accessible to all the other natural sciences departments, I really have opened it up to the natural sciences department at UD, which include brain science and geography and spatial sciences, etc. And in the School of Public Policy, I teach a class called Generating and Interpreting Evidence for Evidence-Based Decision in Urban Environments. So essentially thinking about the evidence in evidence-based decisions. And I've also exported some of these into modules abroad. I was teaching a class in Italy called Machine Learning for Natural Scientists last semester. That's a graduate class. And I might be teaching it again next year. The challenges here that I faced were different, but like I said, in the classes in public policy, in urban science, the challenge is really the diversity of students. There are students that come in as absolute coding novices, and there are proficient hackers, there are data enthusiasts, and there are people that are really in for the domain experience. When I teach physical scientists and to natural scientists, the challenge is a bit different. I find that these students are very used to separating the classroom work from the research work. And I try to integrate them into a project-based module that they're less used to, particularly at the undergraduate level. And here too, some students have very, very basic coding background, very structured coding background, and some students are used to coding for research, which is a bit different. And finally, when I teach in Europe, it's the challenge is that students are actually much less accustomed to participatory work in the classroom. They're very used to, at least in Italy, to still sit back and absorb a lecture and being talked to, as opposed to make it interactive. And so the effort is really shifting towards interactivity. I see data science as really an opportunity for enhancing inclusivity in STEM. I think that we can leverage data science to make physics more accessible to a lot of students by leveraging their backgrounds and their experience and their technical skills more broadly than if they already come from a physics trajectory. So I really care about making my classes accessible to physicists, but also more broadly to people that are interested in STEM, but maybe intimidated by STEM. And along this line, we're developing a multi-department program at the University of Delaware that is really designed to get students from all the departments. It's really hard to set it up because it doesn't have a department of home, and administratively, these things are really hard. And we're working with two historically Black colleges and universities, Delaware State University and Lincoln University. And so the focus again is to make it interesting for students that have interest in the physical sciences and in the natural sciences, but still accessible for students that don't have a scientific background. The sort of recipe that I come up with for this is to always use exclusively real data and real problems. I don't have any mock examples. I don't use the default data sets that are accessible through sklearn, no IRIS data set. These are always based on real world problems. So in public policy, that might be open data sets about policy issues. I don't know, city bikes is one of the most popular one, or Uber rides, or census data. And in physics, this generally means hunting down papers that are reproducible and extracting chunks of the work that has been done and have the students reproducing it. And the most consuming aspect is to actually find papers that are reproducible and not just claim that they're reproducible, where the data is actually accessible and the code is actually readable and works. All the classes that I teach are try to be very collaborative. So the homeworks are essentially small collaborative projects, and generally the final and midterms are relating to a project. And I use exclusively freely accessible tools that are industry ready. So the students build a portfolio for the industry if they shift out of academia. I use Slack or Discord for class communication. I help the students build a GitHub portfolio by delivering their homework exclusively through GitHub. We code exclusively on GitHub Collab, on Google Collab at this point. I'm not sponsored by Google, but being able to code on a platform that is freely accessible online for all the students really reduces access to technology issues. So it's really, I think, the most equitable way to do this. And I focus on a single language in all of these classes, and it's always Python because I'm the most comfortable with it. I think doing it in R would be just as fine, but I think it's important to do a single language to help them becoming proficient on the details of at least one language. And I also always always have lectures and discussions, and I invite data science ethics and ethics of AI, and I invite speakers to my ethicists to speak to my students very often. And finally, maybe if I have one more minute, yes, I will talk about grading. So I generally, like I said, all the homework are small projects, they're Python notebooks. The students receive a skeleton notebook and essentially complete it. Sometimes I include some of the figures so that they can see that they're on track on reproducing the analysis, but I don't grade them on the coding. It's very hard to grade on coding. It's very time consuming. I don't feel comfortable leaving that task to TAs. And ultimately, these are classes on data science and not on coding. So I think what's really important is to be able to interpret the analysis. So I came up with this grading scheme where really the only thing that I grade are the figures. Do the figures look like the analysis is correct? And the figure captions. So I require all the students to describe the figures and interpret the figures. So this shifts the emphasis from being able to code data science to really understanding and being able to interpret the results of models. And I enforce reproducibility, so the students' notebook have to run, I have to be able to run them directly without bugs. I often, I just introduced this recently, but for the final project, in addition to having presentations, I have a one-on-one interview with each one of the students that can tell me their experience about the project, and also gives them the opportunity to tell me about their experience in class. This is something that I carry from my European education background, where that's how we were doing exams. And I was intimidated by bringing it to the US, but it worked out fairly well. All of my material is public. Some of it is even not too terribly poorly organized. And so here is a bunch of links to my slides and GitHub assignments and homeworks and projects, etc.
All right, thank you, Frederica, for all of that. I'm definitely interested in talking with you about your grading, but for now we'll move on to our next speaker. So our next speaker is Boris. He's a professor at Harvard, where his research centers around machine learning and electronic structure calculations and atomistic calculations. He's also appeared at a number of our tutorials for the topical group on data science, along with his student. And with that, Boris, excited to hear what you have to say.
Great, thank you. So just a quick overview of what my area is. We are a computational science group working in the materials science, so which means that we try to understand materials down to atomic level. So all of the things that we do deal with atoms and electrons, and we put these simulations on large computers and try to apply data science and machine learning techniques to accelerate materials design, to accelerate understanding of materials with these techniques. So the questions that arise in our field that basically can be summarized in this slide. We have a lot of data that gets produced by simulation. So computational science produces data there, and how do you deal with that data is question number one. How do you manage it? In other words, once it's produced, how do you store it so that it's findable, reproducible, reusable, all these nice things that we want our data to have. And the second question is, how do you actually use that data? How do you train models that can accelerate discovery of new materials, accelerate simulations of materials properties? And these have to do with machine learning. So there are these two aspects that we try to address. And my approach has been developing tools for these challenges, and then making these tools open source, and then providing training to any sort of users in our community, which is fairly large, that wants to simulate materials accurately and quickly. So the first question is, how do you manage the data? When I was in industry, I spent 10 years at Bosch Research before moving to Harvard. I started this project called AIDA, which essentially is aimed at making this process of generating data painless, so that you can do high throughput calculations, annotate everything automatically using Python workflows, and that every data piece, every data flow is automatically captured in a graph database that is then preserving the entire chain of events. And then you can search and figure out what's good, what's not good. Then you can plug in lots of codes in it. So it's an ecosystem, really, and now widely used and coupled to the materials cloud. It's an effort in Europe that's based on this infrastructure. This is just one example of a solution that was sort of driven by our industrial project needs. And then we spun it into an open source project together with the EPFL. And now a lot of training opportunities are available in terms of workshops and schools and things that sort of educate people in using these kind of tools so that they can painlessly apply high throughput calculations to their problems. The other approach that we've most recently started following is using machine learning to accelerate calculations of atomic motion. And this is, again, a very wide range of applications, because essentially if you study catalysis or ionic transport, a lot of problems arise where you want to study reaction dynamics, transformations of phases, things like that. So tools we have developed are in this arena based on neural networks and Gaussian processes and active learning, and some interesting sort of symmetry models that are being built. Again, these are open source tools now for which we hold tutorials at conferences and educate the new generation of users, because this is going to change, and it's already changing the way we do computational material science. Machine learning has really transformed how accurately and how quickly we can understand materials. So again, these are sort of things that you can look at as examples, but summarizing what sort of the approach of educating people in our community in using data science and using machine learning has been through, first of all, solving challenges that we have, and then providing these solutions as open source code with exhaustive documentation, lots of examples, so that these sort of very generic tools that can be applied to any material science problem can be used by users who don't have that much experience. The other components, of course, we hold tutorials at conferences, at MRS, at APS, and European SICOM workshops, and some of them are available on YouTube. And again, making it as easy as possible to start, let's say, using the Flare code. We have Collab notebooks. We've done 2 or 3 tutorials at various APS March meetings. And what I want to emphasize is also all of this is being introduced in graduate and undergraduate curriculum. So I have this course that I teach. I started teaching it at MIT. Now I teach it at Harvard, that basically teaches all these techniques to students who are half experimentalists, half computational students, but they learn about machine learning in that course in the context of material science. So it's very sharp motivation that provides sort of a background for what they're learning, why this is useful, and all these modules and application of machine learning to material simulation. They're being taught in a hands-on way. In other words, students get assignments which are actually written using Python workflows, so that all the data management or sort of workflow management aspects are taken care of for them, and they learn sort of the best practices there. And they also get to play with machine learning models in designing materials in their final projects and in producing sort of simulations in the state-of-the-art level. And again, the motivation here is emphasized that they work on realistic materials, so they actually simulate things like graphene or aluminum atoms on aluminum surface and these kind of things. So very specific, very targeted kind of realistic applications to provide extra motivation for learning data science. All right, that's all I had. Thank you.
All right, thank you so much, Boris. And let's see, again, for those of you who are asking questions about the various things, then you can ask the questions in the Slido. This is just there, and there are a number of questions about links to Slack and such. We will keep posting those in the chat, and there are also links to in one of the questions on the Slido. So with that, we'll come to our final panelist, Mohammed Sultana. He is the founder of the topical group on data science. He's had an interesting career where he's been in industry, he's been in academia, and he's now actually in the business school at Boston University. So I think he'll have a very unique perspective to share about data science education. Thanks, Mohammed. Please, excited to hear what you have to say.
Thanks, William. Thank you for organizing this fantastic webinar. I've been enjoying all the talks. As William mentioned, I am a clinical assistant professor at Boston University's Information Systems Department. I am also a faculty expert at Google Cloud, and I'm here today to talk a little bit about the technical aspects of data science education and particularly using cloud computing for your courses as well as your research. As William mentioned earlier, about 4 years ago, along with Dr. Jay Wren, I founded the topical group on data science at APS. And then we kicked it off the ground with the help of people such as William, Wolfgang, Maria, amazing group. And it's fantastic just to sit back and see it is growing so fast. If you're not an official member of the GDS, I encourage you to sign up. They can directly support this amazing and the fastest growing group at APS. Why I believe it's just $10 a year, which enables events such as this. And also our election is coming up. If you're a member, make sure to go ahead and vote. All the thoughts I share here with you are my own, not none of the organizations I represent. I'm also not financially affiliated with any of the companies that I present their tools. Very briefly, you only have a few minutes here. I'm going to talk about the code sharing and content delivery tools, which already people discuss, and I assume most of you already are working with GitHub. Software and computational resources in the cloud. I'll talk data sharing as well as open data sets available for your students. So GitHub was mentioned multiple times. You can get a free premium account going to education.github.com. Great source for sharing your code, the course content with your students, also allowing the students to collaborate with each other for the projects that are attached to your course. If you're interested to see the course materials that I have, all of them are public in my GitHub. Here's the link, just my last name. And moving on, the content delivery, also Collab was mentioned repeatedly by almost all of the speakers. It's a great free source that allows the students to work on one of the Google Cloud's virtual machines, and it's seamless. You can just basically go in, such as a Google Doc, and Google gives you a temporary virtual machine, and all the students have Python and a lot of data science libraries pre-installed. So it's fantastic, a lot easier than asking students to install Python on their machines. I'm going to skip the other ones. Let's get to cloud computing. There are a lot of different cloud providers out there. I will be focusing on Google Cloud Platform, the one that I'm most experienced with. And I have my previous job as data scientist in the industry. I worked with AWS also, but I'm a true believer of Google Cloud because it allows a lot of freedom to you and also to your students. So first of all, why cloud is cost effective and is highly scalable. You can customize the machines that are you're using, and it has a lot of applications in IoT, in AI, databases, and serverless. So you can focus on the problem you're solving rather than trying to maintain the hardware and the software behind. And why should you care for cloud for your courses? Isn't it something that the companies only use and national labs? Not really, because it will come with a lot of benefits for you and your students. Almost zero setup time, less debugging. All the students will have access to the same software and hardware, which means that whatever code you have, once it runs, it will run for everyone. It is independent on the operating system. and other hardware configurations. All the students will have to the same compute power, so it brings some sort of equity to the students, regardless of how old their laptop is. All they need is a browser, an internet connection, and then all the compute is happening in the cloud. And it allows you for your research and also for your students to scale up. Collab is great, but it's pretty limited. You get to get access like to 16 gigabytes of RAM. It's 8 or 16, the free version. I forgot, 4 CPUs. And with Google Cloud, for instance, or any other cloud provider, you can easily scale up vertically, and also you can scale up horizontally. So it's especially for research problems, you would want to be able to scale up. Students will learn marketable skills and while learning the science, convenient for sharing data sets, and allowing students to work together. The cons could be the billing. So there is that component that if they're using their laptops, they don't have to think about, but here everything costs. But for instance, Google offers grants. I will talk about this briefly at my last slide. So you can get compute resources. For instance, Compute Engine is a service that gives you virtual machines. Basically, you get a machine that you pay per seconds that you use, and you can highly customize that machine. There are all sorts of storage solutions, such as cloud storage, which is like a scalable Dropbox. You can store all sorts of data files, but also SQL services and all sorts of storage solutions. For big data, BigQuery, for instance, is a scalable database that you can put petabytes of data there. And it also supports machine learning. For machine learning itself, there's an array of resources, either from the pre-trained algorithms that Google has trained, or you go to other cloud providers, Microsoft or Amazon, they have trained. You can use, such as Translate, such as speech to text, image recognition, things like that, or there are services that you can train your own models in a scalable fashion. One of the reasons I prefer Google Cloud over other ones is that it allows you to have projects, and each project is attached to its own billing. So I have one project per course I teach. I also have one project per research that I do, and it's very easy to define collaborators, so everyone will have access to the same resources. Also define billing, so you just separate all of the billings from each other. And then that's a project organization, which is a logical organization. There's also a physical organization, that where your data is located, where your hardware is located. The structured versus unstructured data, I will share my slides. So here's a diagram to guide you. If you have unstructured data, cloud storage would be a great solution. If you have structured data based on what you want to do, you might be using any of these solutions. This is an incomplete picture, but it's a good starting point. For big data tools, there's a lot of support. For instance, Spark is the still growing solution that the industry is using, and there's a lot of support for that. For instance, Dataproc is a solution in Google Cloud that offers Spark support. For machine learning, depending on where you want to be, as I mentioned, there is support for every piece of it. If you want to just do like friendly machine learning using the APIs, or you want to build your own TensorFlow or PyTorch from scratch, you can get the resources. And I believe finally, I just want to briefly talk about the grants that you can apply for Google. There, you can go to this link, and for every course that you teach, you can get $50 per students. It's a free cloud credit. And for your research, you can also apply and get up to $5,000 research credit and per year. So this is per course, the $50. This is per year for your research. Quick Labs is a great tool that allows you still have to pay, but you can get 5,000 credits, which is equivalent to $5,000. Allows you to assign assignments, labs to the students, and the students will get instructions, for instance, how to set up a virtual machine and how to, run a machine learning pipeline. And all the instructions are there, and Google QuickLab, which is owned by Google, they give the students a temporary cloud environment that the students can apply the instructions there and learn instead of using their $50. So it's a great resource. AWS Educate, they offer one-time credit per students. So this is a little bit tricky because it's one time. So if they have a second course, they might run out of the credit. That was one of the reasons I used Google, on top of the fact that it has that project concept that AWS doesn't have. Microsoft Azure also gives the students a one-time $100 credit. Again, this is, at least to my best of my knowledge, these are one-time credits. They're not per course, but Google's are per course, but you have to apply. The application is very easy, and but you have to do it a few weeks in advance, maybe like 6 weeks in advance of your course. All right, I'm going to stop here. No, we are almost out of time. Thank you very much for your attention.
All right, thank you so much, Mohammed. And so let's leap right into the question and answer. And so one of the most popular questions is, what kind of background should the students have to do data science? What's the bare minimum set of skills that they need to participate in these activities? So anyone from the panel? Looks like Gilad wants to say something.
Yeah, so what I found is that it's very easy for, you can even get high school students to accomplish significant tasks using machine learning because of the very easy resources that exist from scikit-learn and Collab and all these other resources. So teaching basic intuition, you don't really need that much background, but to get to the level of being able to come up with your own algorithms, at that point you need to have good linear algebra, statistics, and sort of solid math foundations.
Let's see. So any of the other panelists, like Federica, you have a very interesting cross-section that you teach.
Yeah, I think there is an intermediate stage between the two stages that Gilad described, right? So it's true that you can basically throw the students a data science problem, giving them enough guidance, and the machine learning models are easy enough to use in Python that they don't really need to know much. And then it's true that they need the solid mathematics and linear algebra and statistics background to develop algorithm, but there is an in-between where they can be users of algorithms, but really knowledgeable enough to understand what the algorithms do and therefore interpret the results, and then deploy what they're learning for job or research very effectively, right? And so for that, I think what I find that the students really lack, so they need some basic coding, otherwise you spend the whole time teaching them just how to code, but it's really basic, and I can get away with like a 1-day boot camp or 2 days boot camp and give them enough. Of course they will have to spend enough time on the homeworks, etc., but it will be enough. What I find that the students lack the most is basic statistics, like understanding what is a distribution, understanding confidence, what does it mean to talk about confidence intervals and the confidence of your results, even combinatorial statistics. So those are the things that I think are generally lacking in the background of the students, like a really intuitive understanding about that, both in the natural sciences and in the social sciences. In spite of ostensibly both should have that training.
Yeah, thank you. I mean, yeah, in general, my impression has been is that physicists are very good at probability, but statistics, well, there are some that are much better than others. Like at least some fields that were trained more than others. Now, one other question in the Slack, sorry, in the Slido that I think a number of you have already sort of answered is, what are some low-cost, low-barrier ways for faculty to get started, including data science in undergrad physics courses? And I think you've all mentioned the use of cloud resources, like especially Mohammed, to make this sort of free to almost free in terms of cost. But what about the low barrier part?
I can comment on that. I would say for the faculty to get started, you definitely want to have some experience before starting to implement these cloud tools in your classes. I would say moving some of your research, if you're a researcher, to cloud, that would definitely give you a head start. And a tool or service such as QuickLab that I mentioned, that allows you to do little projects. That the QuickLab projects take less than 2 hours. In fact, they give you 2 hours of time to complete. Within 2 hours, you will get comfortable enough with one of the services that they're offering, so you can just follow the instructions. They're designed to be self-guided. I would say for cloud, that would be the best way to start, and bringing your research also into that space. I hope that helps.
Okay, I think that's very discreet. Does anyone else want to comment?
I think I could maybe add the existence of good data sets. So in research, you can spend quite a lot of time cleaning your data. That may not be so interesting for learning data science, though it's an important part of it. So providing a data set that's easily accessible for students is valuable, I think.
And I think that's a nice segue into another question, which is how do you cater the training to physics majors to distinguish data science training from, say, what they would receive in, say, a CS department or statistics department or business school? Oh, great, Gilad.
So definitely not a focus on proofs or bounds of the algorithms. Students are not interested, like the physical scientists that I've worked with, the students, they're not interested in looking at proofs or bounds or proofs of bounds, but more just focus on demonstrations and getting intuition as to what are the limits of the different algorithms, when to use different algorithms, that kind of thing.
Okay, great. And I think also a number of you have mentioned the importance of working with real data and how that also really helps with the students. I mean, like I've heard both Boris and Frederica mention that this idea. There are a couple of minor. Go on.
Can I just say one thing about that? That I saw that there's a bunch of questions on Slido about like, what is the difference between computer science and data science, right? I think a lot of it is exactly in what you said. It's in the use of real data and what Trevor said, like learning how to clean the data and prepare it. It's something that is much more common in the data science, like in the applied data science than in the computer science disciplines.
And Mohammed.
Just very briefly, speaking of using practical real data, domain specific, if you haven't heard of Kaggle, kaggle.com, that's a great platform that people share their data, either research data or competitions, and you can direct your students there. Once they get something, data set that they're interested in, that area, it's going to motivate them to learn all these methods.
Okay. Now, there are a couple of questions related to the boot camps. So if those who are running boot camps could put the information in the Slack channel, then that would be great. We'll post the Slack links again. We'll also mention them in our email. So if you join our mailing list, you'll get the information there as well. But there are some questions about the boot camp. So if people can post those, then that would be nice. So there's another question that sort of came up. Which is, like for small undergraduate-based institutions in which the professors maybe have some computational experience, but not so much data science experience. Do you have any recommendations for them on sort of how to get started in terms of teaching this or including this in their classes? Okay, Mohammed.
Just a DSE Cup, that is basically the grant that William mentioned that was recently received from APS. Its top priority is to create some data science modules that you can take these modules and bring them to your classes. We are just getting started. And once these modules are out, you will hear communications from us. Everything is going to be open source on GitHub. And I hope that will help you to get started with the implementing data science components to your existing courses.
So I'd like to add to that. I don't know if it would be useful, but this curated list of online resources that exist at the REMI website. There is the possibility. One thing we're interested in doing is filtering through those to identify, Jupyter notebooks that are very easy to modify into modules. So that could be an avenue for quickly identifying, templates for modules. So I don't know if it would be useful, but potentially.
Okay, great. So just as a note, as we begin to run out of time, I'll post some of these questions that we haven't reached on the Slack, so that, and I'll ask some of our panelists if they don't mind answering them on the Slack there. Then I think that will also allow us to continue the conversation. I think at this point we have time for one more question and then a closing comment from Wolfgang. So for this final question, there are sort of two thoughts of how do you define data science? Now, this is a big question, but basically, how do you distinguish it between, say, the computation that some people are doing in classes? Yeah. So, any thoughts on this in general? Where are your boundaries for data science?
I can connect that to what I said earlier. I think really it's critical that you use real data sets, because data science is really about real applications of algorithms. And then when I think about data science, I think there is a bit of confusion between like what is data science and what is machine learning. So when I think about a data science class and when I call my class data science, I definitely include more basic statistical analysis, even like p-value statistical analysis, especially in the social sciences. And I think that definitely qualifies as data science. I also always try to include at least some machine learning, because it keeps the students engaged to have that as a goal, to be able to run a neural network or a random forest, even at the end of a class where they had never done any serious data analytics work.
Yeah, I just wanted to comment on this as well. In my perspective, data science starts after you already have data from some source, either measurements, experimental collection statistics, or computational. That's sort of domain science, which produces the data. Then there is a question of how you store and manage that data, which I think is often sort of overlooked, and people jump straight to machine learning, but that's all good. And regression and trend analysis is definitely part of data science now that the data is there. But that middle part, how do you actually manage, curate, organize, search, all the database technology that also needs to be there for big data, it also belongs to data science. So I would put the boundary from sort of the first sort of domain which generates the data, and then data science begins with management and proceeds with analysis, with machine learning, regression techniques, and so forth.
Okay, and so with that, I think that we need to sort of bring the panel to a close. I see that there are a lot more questions on Slido. And so, as I said, I'll put those in the Slack. If anybody has trouble with Slack, just feel free to email me or any of the other PIs, and we'll be happy to try and get you sorted. But, do try just clicking on the link first. And with that, we have one closing word from Wolfgang.
I wanted to, as the chair of the group on data science, I wanted to thank you all for being so interested in bringing data science education to the physics curriculum and being part of this kickoff event for the Data Science Education Community of Practice APS Innovation Fund project that William is leading. And I wanted to thank APS for their support through the Innovation Fund of this effort. And I wanted to thank our Institute for Physical Science and Technology at the University of Maryland for supporting this effort as well. And I hope you'll be very interested in being part of the community, taking advantage of the modules that Mohammed mentioned, and staying engaged. And so please do join the mailing lists and contribute everything that you know already and everything that you're interested in. I did want to end by really thanking William, who has been leading the effort and has started us on this path to build a data science community and of practice. So please join me in a round of applause for William and thanking him.
And thanks for all of our panelists for agreeing to take the time out today, and also for all of you who took time out to learn a little bit about this. And I hope that you join our community. So with that, I believe that we are on time. As I mentioned, I'll post the remaining questions in the Slack. If you join our mailing list, you'll get an announcement about when the video is posted on YouTube. And with that, thanks.
Thank you.
Thanks,
Thank
William.
you.
Thanks, everyone.
Thanks, everyone.
You.
Good to see you all.